Hello everyone. If you haven't met me before, so if you haven't seen my non-imaging analysis lecture, my name is Dr. Luca Matra and I'm a lecturer at the National University of Ireland in Galway, Ireland. So in this primer to data reduction, we're basically going to look at the imaging step of our SMA data. And particularly, we're going to focus on imaging in the Casa software package as developed by NRAO, and is also used to image data from other interferometric arrays, such as ALMA, for example. Okay, so, oops, sorry about that. Here we go. Okay, so just in the first few minutes, I just want to recap what you've seen before about imaging, just as an introduction to what we're going to be doing in practice next, which is the goal of this tutorial. So in this overview of the imaging, so first we have a step that is, in imaging, we have first a step that is gridding, weighting of the visibilities, and inverse Fourier transforming to obtain the first dirty image, which is simply the Fourier transform of our calibrated visibility function. Remember, we've already calibrated the visibilities at this point, in particular in the MIR software package, usually for SMA data. And now we want to go and create images. So the first inverse Fourier transform creates the dirty image. And then the second step, because this image is so-called dirty, as you will have seen from your imaging lectures, then you're going to have to carry out some deconvolution, for example, to the clean algorithm, and to produce some cleaned images, which will be a better representation, a cleaner representation of the true image that you're trying to obtain. So the goal is to obtain an image from calibrated visibilities that is as clear of artifacts and as accurate a reproduction as of the true sky-brightness distribution as possible. Now, disclaimer is, of course, again, as you will probably seen, that the deconvolution, it can be considered as a modeling process, and because of the incomplete UV coverage, so basically we're only measuring visibilities at these discrete points, and we don't have information all over this UV plane. What that means is that there's an infinite number of models that can actually fit the visibility data, because we don't have information in locations in UV space that we're not sampling through our interferometric array. As was probably mentioned in previous imaging lectures, things to keep you awake at night. So in other words, there's not a one-to-one relation between your calibrated visibilities and the final clean image. There's an infinite number of images that can be fit to your visibility data. But the idea is that we want to get a reasonable approximation to what the true image distribution looks like. Okay, so here's a recap of how the imaging process takes place. Okay, so let's focus on the left-hand side, and please bear with me in these steps. So the first steps, as I said, is gridding plus weighting, and then the first inverse Fourier, and then inverting, so the first inverse Fourier transform to obtain the first images. So we've got a real and imaginary part of your sampled visibilities from your interferometer that have been calibrated, and what we do is we want to grid them. Okay, so we want to put them on a 2D grid so that we can apply a fast Fourier transform algorithm on them. Okay. And some weighting goes on at the same time, so you can upweigh longer baselines compared to shorter baselines, or vice versa. And you will have gone through different types of weighting again in previous lectures. And then in the first step, we inverse Fourier transform these gridded, calibrated visibilities to obtain a first approximation of your image, which is the so-called dirty image. Now, what is this dirty image? You can actually interpret this dirty image as being the true image convolved with a dirty beam. Sorry, the two convolution symbols came out here, but anyway, it's the true image convolved by the dirty beam, gives us the dirty image. Now, what is the dirty beam? What do I mean by dirty beam and true image? Okay, so as we said, the observed visibility function, okay, is a sampled version of the true underlying visibility function. So the true underlying visibility function will also have a real part and an imaginary part, okay? And if you gridded that and you inverse Fourier transform that, you would get the true image, okay? But that's not what we have. We've only got sampled and noisy visibilities that we inverse Fourier transform to obtain a dirty image. Now, the UV coverage, which is what I was showing you in, for example, this diagram here. The UV coverage is if inverse Fourier transform gives us the dirty beam, okay? And then the true image combined with the dirty beam gives us the dirty image, because basically the true visibility is multiplied. This is a Fourier transform properties. A convolution in image space is equal to multiplication in visibility space, because the visibility, the true visibility multiplied by the sampling function, the UV coverage, gives us the sampled visibilities. Okay, right. So we're trying to make as good an approximation as possible to this true image, but all we have is the dirty image, and then we know also the dirty beam. Okay, so the idea is to use deconvolution to try and get an approximation of the true image from the dirty image, knowing the dirty beam. Okay, so that's what we're trying to do. And this deconvolution takes place typically through this clean algorithm, and I'm going to describe here the Hogbone clean algorithm, classic Hogbone clean algorithm, where basically what we're trying to do is we're trying to represent our dirty image or our true image as a sum of point sources. Okay, so even if you have extended emission, we try to reproduce that as the sum of unresolved point sources. Okay, so that's how clean works. So in a minor cycle, so we have clean cycle iterations where we start from the dirty image. Okay, so this is the dirty image, for example, of this source, which comprises of a ring and a point source down here. Okay, and you can see that this image has a lot of side lobes. It's very it has all this artificial structure that is simply due to the sampling, the discrete sampling of the visibilities. Okay, so what we're going to do then in the clean algorithm is first we're going to draw a mask around the regions where we think the emission lies. So in this case, we'll draw a mask that comprises this ring and a mask that comprises this point source, because we think there's true emission there. Okay, and what clean will do it will basically find the peak in flux, in surface brightness, the peak surface brightness within these masks. Okay, in this case, the peak surface brightness will be at the location of this point source, and what it will do is it will create a model, and this model will be a single point source in one cycle. It will create a point source with a flux density that is just a fraction called the loop gain gamma, a fraction of this maximum intensity or surface brightness I max. Okay, so just to recap up for now, we take the dirty image, we draw some masks, we find the peak intensity, and we create a clean model that to begin with has a single point source, represented here by a single pixel. Okay, and what clean then does is it convolves this model, this clean model, currently just a single point source. It convolves it by the dirty beam. So this is the dirty beam. You can see that it has a core that looks like a 2D Gaussian, and it has some side lobes, which cause the beam to be dirty. This is simply, as we said before, the inverse Fourier transform of the UV coverage. If we convolve that, the point source by the dirty beam, you obtain basically a dirty image of the model. And if you subtract this dirty image from the model, okay, you obtain a residual image, and this residual image will be the same as your initial dirty image, but with some of the intensity of your source, which will correspond to the previously maximum intensity, removed. Okay, so in this image, you can see that some of the emission from the point source has been removed because that emission has been added to the clean model. Okay, so once we get to this residual image, it's kind of like you can see it as sort of a fitting procedure. So once you get to this residual image, you ask yourself, does it look like noise? Does it look like we have removed all of the emission from our astrophysical sources? If the answer is no, which it is in this case, because you can see that there's still emission that probably arises from physical sources, this image doesn't look like just pure noise, then we will say no, and we will repeat the procedure, okay? So basically, instead of having the initial dirty image, now we've got this residual image. In this residual image, we'll have our masks, and once again, we'll find the peak, add that peak flux multiplied by loop gain to a model, convolve by dirty beam, obtain a dirty image of the model, subtract again. And we keep basically adding to the clean model and then subtracting off from our residual images all the time in this interactive fashion. Okay, and we do that all the way until this image looks just like there's only noise there. There's no astrophysical emission. And when it does finally, okay, you end up with having a final model. Remember, this is a clean model. But once you've added all of these point sources, once you've added a lot of point sources, it will look like this. It will look close to what we expect our sources to look like. But remember, it's only an approximation because it's a sum of point sources, okay? So this can be bad sometimes at reproducing very extended emission. So we end up with a final model in this case, after 7,800 iterations. So we went through this iterative routine 7,800 times. How many times you have to do this depends on how much flux there is in your source and how complicated your source is, etc. So we can convolve that. And so what we do at the end, we end up with this final model. We convolve that by the clean beam. Now, this is not the same as the dirty beam. So you see, here's the dirty beam. You can see the dirty beam, which is just the inverse Fourier transform of UV coverage, once again, has a lot of side lobes. Okay, so the flux is not all concentrated in the center. It will be also spread around the rest of the image. So what we do is we convolve that by the clean beam, which is an idealized approximation of, it's basically the core of the dirty beam. And then we add the final noise-like residual image, which was the residual image that we obtained at the end that looked like noise. So we were happy with it. So we add the noise to it, convolve by the clean beam, add the noise to it, and we end up with a final clean image, which is, as you can see, much cleaner compared to the dirty image we started with, and a much more realistic representation of our true image. Okay, so that's the clean procedure. But before we go into cleaning, you have to first import the data to Casa and inspect the data to make sure everything is fine and to recognize any errors that may be still in your data after calibration. So how do we do it for SMA data specifically? The calibrated data from MIR can be exported to Casa via the UV fits standard. And there's a step-by-step instruction at this website. So within MIR, what you want to do is you want to run the auto fits routine on the target visibility data. And that outputs UV fits file containing your calibrated visibility function. And it will create one file per chunk, per sideband, and per receiver. Okay, this routine can take a little bit of time, so just warning you here in case you're following this for your own data reduction. So then you want to open Casa, and you want to import this mirfits to casa.py script, which you can find again at this web page. And this is basically a script that I wrote that basically allows you to properly import a UV fits file to create a Casa visibility measurement set. So this is basically the standard file where visibilities are contained within the Casa software package. Okay, and you want to run that script on all of your UV fits files, which you then want to concatenate to end up with a single finalized measurement set with all of the chunks, all of the sidebands, and all of the receivers. And then what we want to do is we want to inspect the data with list obs and the plot MS task, flag back channels, and prep for imaging in general. Now, if you want to do continuum imaging, if you're trying to do continuum images, what you want to do is you want to flag spectral channels where you have a lot of line emission. Okay, so if you have strong line emission, you will want to flag those channels before you and I create the continuum, because otherwise the spectral line will contribute to your continuum, which is not something you want in most cases. You can do that using the plot MS, as we will see, and then we want to average the channels. We can average the channels all together because we're only interested in continuum, so we can average channels together already in the visibility space before imaging, for example, using the split or MS transform Casa routines. And you can do this to basically significantly reduce the number of visibilities and speed up the imaging. Time averaging may also be useful. So remember that, for example, the SMA could take scans every 5, 10, 30, 60 seconds, depending on what you chose when you wrote your observing script. So there's one visibility for every baseline for every one of these scans. Okay, so if your observation is 8 hours and you've got like 5-second scans, you end up with millions and millions of visibilities. So you can average these together in time as well as in frequency if it helps to speed up the imaging. However, you should be very careful because averaging time and frequency can lead to time and bandwidth smearing. Okay, which you want to avoid. And I'm not going to go into the details there, but you should look, for example, at the Thompson, Moran, and Swenson book, this section in particular. So this is just showing you why that's going to happen. Because remember, these tracks in the UV coverage are basically different point in time, so different times. And these parallel tracks, each of these 4 parallel tracks, in this case, correspond to 4 different frequencies or spectral windows. Okay, and so even though you have the same baseline antenna pair for all of these points, they have all different frequencies at different times, creating these parallel tracks. So if you average these together, so if you average in time, you're basically smearing all these points. From all of those points, you're creating a single data point. And similarly, if you average in frequency, you're creating a single data point for all of those frequencies. So what's going to happen is that you're going to reduce your UV coverage, and if you reduce it too much, you're going to affect it in a way that you don't really want. So you should be a little bit careful about that. But usually for SMA data, we can average all the frequencies together within a single chunk at 230 gigahertz at least. So if you want to do line imaging, on the other hand, what you want to do is you first need to subtract your continuum. Again, if you want, in most cases, people will want to, using the channels by fitting the continuum like you would do a baseline fitting for single dish radio data. You want to fit the continuum in channels away from your line, okay? And you do this in visibility space for every antenna pair at every time and every frequency using this UV console Casa task, okay? And finally, again, you want to average in time if needed to speed up the imaging. And finally, you want to use the T-clean Casa task to basically which carries out all of the processes that we talked about: gridding, weighting, inverse Fourier transforming to create a dirty image, and then the deconvolution. So the T-clean Casa task does it all in one. So it's a bit of a monster task, but we can break it down, and we will in this tutorial, and try to understand what's going on within it. Okay, so let's do it. So here I've got my terminal, and by the way, this folder containing the data and the imaging script, which is the script that I've created here to guide you through all these steps that we just talked about, is available to you within the lecture slides if you just click on this link. So you can repeat these steps to familiarize yourself with the whole process. Okay, so the first thing, I go to my terminal and I start up Casa. In this case, so this works with Casa version 5.6.1. So the first thing that happens when Casa opens is that we see the log appear. So this is the Casa log, and you want to pay special attention to it because it prints out some very useful information as you carry out different tasks. Now, the first thing about Casa is that it's an IPython terminal. So you can, create variables, assign them some values. You can print stuff. You can basically act as if it's just a IPython terminal, which is really great. And So the first thing we want to do, so here's an example template script that you would use for your imaging. So the first step is this basically importing the data into Casa from your UV-Fits files that you would have created with the AutoFits routine within Mir. Okay, so let me see. So if I show the data folder where I'm grabbing this data, so I've already done this. So you will see that there's a bunch of UV-Fits files. Okay, so there's a UV-Fit file for every chunk, S1, S2, S3, S4, for every sideband, lower L or upper sideband U, and for every receiver, RX230, 230 receiver, RX240, the 240 receiver. So this was taken at a time that the SMA had 4 chunks per sideband per receiver. Okay, so I will have created these through the AutoFits task within Mir. So now the idea is that basically we want to import these into Casa and create a measurement set containing our visibilities. And you can see that I've already done this here. You can see that .ms files for every single one of these UV-Fits files, I've created an MS file. And I've done so through this loop here, where basically given my source name, HD127821, the target of this observation, for every receiver, for every sideband, for every chunk, I'm basically giving them a name. I'm going to print something, and I'm basically using, this is the key line here, where we basically use this Mir fits to Casa file, which it's a Python script that you should have in your current directory, which I think I do here. Hold on. Well, I don't here, but you should have it in the current directory. Oh no, here I have it. I have it in this directory here, which I appended to the path, so it will know it will be able to import it here through this line. Okay, and so then you run it on every single UV-Fits file to create an MS file, and then I basically do an ls here to list what's in the current directory, and that's what I just did there for you. Basically showing that this went well and you've created an MS file for every UV-Fits file. And then the next step, I'm going to concatenate all of these MS files. So the concat is a Casa task that you can use to merge different measurement sets, so merge different visibility data sets. In this case, we're merging all of the different data sets from the different chunks, different sidebands, and different receivers to all be in a single data set that we can then handle. Okay, so I'm just going to run a few of these lines. I'm not going to repeat this this creation of the MS data sets because it takes a little bit of time, and for the interest of time, I'm not going to do that here. And similarly for the concatenate time. So, but I will start from here. I will start from this listobs command. So this listobs command is really crucial to understand the structure of the data and to basically find yourself when you're kind of lost in what's going on with your data. So here we're on the listobs command, and you can see here that it gives us a whole lot of information. I'm just going to expand this a little bit for clarity. So you want to look at the log. It says, for example, so here is where it starts, begin task listobs. This is how we called it with the standard parameters. It tells us that the observer is me, that the observation was done with the SMA, and there's several parts to this structure. So it tells us here that it was observed from this date at this time to this date at that time, in UTC time. So here is basically a time log of the observations, where it says basically that the data is divided into scans, and what for different scans, what are the time ranges. Then it basically tells us what field was observed. We're going to go into fields in a second. It tells us how many visibilities are in that scan for that field. It tells us what frequency spectral window IDs were observed for that given scan, and it tells us basically what the average time interval was for integrations within that scan. So in this case, it was around 30 seconds for this SMA observation. Now in the fields part, what we see is basically what fields were observed. Now in my case, it's just a science target, HD127821 with its array and deck. But if you had also the calibrator, for example, if you imported the calibrators into Casa as well and you merged everything together, you might have the calibrators here, etc. And here next is the spectral windows. So basically it's the frequency properties of this visibility data. There are 8 spectral windows, which for the SMA corresponds to each of the 4 chunks, for lower sideband and upper sideband. In this case, it tells us that there are 2048 channels for each of these chunks, and it tells us what the frequency velocity frame is, LSRK, local standard of rest. It tells us what the frequency of the first channel is in megahertz, and here on the right, perhaps more important when you're trying to understand your data, is the central frequency. So there's the frequency at the center of the chunk. Okay, and this is the bandwidth, and don't mind that it's negative. I don't think it really affects anything in my experience. And this is the width of one channel in kilohertz. So each channel in this observation was 1.1 megahertz. Okay. Yeah, then it tells us what the antennas were, where they were located, etc. And so some ancillary information. Okay, so this list obs is really telling us what the structure of the data is and where different things are within the MS file. Okay, so the first thing is we're going to flag some edge channels, because if you remember MIR, you only worked with the central channels of each chunk, where you basically removed or trimmed 8% of the bandwidth on each side of your chunk. And so we're going to do the same here in Casa, because this is not retained when you basically transfer the data from MIR into Casa. So we're just going to right away. So how do I know how many channels there are in the data? I've seen it here in the stubs that there are 2048 channels for each chunks. So 8% of that is about 130 channels that we want flag at the edge, and we use the flag data command to do that. Okay, so we're just gonna run this. Okay, and yeah, and you can see in the log that this is working. Okay, and so we flagged about 12% of the visibilities in the data. That's what it's telling us. Now, another task that is very useful is plot MS. Plot MS is how you plot visibilities within Casa. So the first thing we're going to do is we're going to inspect our visibilities as a function of channel to see if there's any problems within the bandpass, and to do a bit of error recognition, which you will have seen probably in other lectures within this school. Okay, so here I've run it as a script command, but you can actually just type plot MS and we'll bring up the GUI, and you can use the GUI. Oh, you can see the GUI. Here it is. And you can use the GUI. Here we go. So you can see that it's loading data, and you can use the GUI to basically just select a file and do any sub-selection that you would like. Okay. So here I've told it to average in time, average all the data in time, and average across all of the scans, and plot the amplitude as a function of channel. So here's in the axes panel is where you tell it what to plot. I'm plotting the amplitude as a function of channel, and I'm plotting it for every spectral window, and which corresponds to every SMA chunk. So this is chunk 0, spectral window 0, spectral window 1, spectral window 2. And again, you can use list stubs to remind yourself which ones those are. Okay, and so we want to flag any badness that we see here. And for example, what is this? This is it looks like a spectral line, but it's very broad. In fact, it's an atmospheric line, so you may want to remove it. Now, in this data set, we're actually mostly interested in continuum, so this won't affect us too much because it will get averaged out together with all the other thousands of points. And so, but it basically corresponds to a region of enhanced amplitude, which is due to the fact that there is enhanced noise at that location because there's less transmission basically through the atmosphere. Okay, but we can go ahead and flag that by using this command here, and we can just draw like a little mask around this region that we think is corrupted or particularly noisy. Here we go, and then we can tell it to flag it by clicking this button. You can see that there's stuff happening in the log. Okay, and here you go. You can see that it's now flagged. Okay, so the rest of it looks completely fine. Again, we don't expect any spectral lines in this data. There might be some badness here. You can see there's a region of enhanced noise. But what we would do really, if we wanted to be very careful, everything is fine in this chunk, is we would compare this to the passband visualizer on the SMA website to basically identify any atmospheric lines or any spectral lines that from major molecules that may be of interest, okay? And now remember, the spectral line won't be obvious in visibilities unless it's very strong. So if it's a very faint line, you won't be able to see it. But that's okay for now. So you can see here there may be some outlying points, but you don't, there's only a few points, so it won't affect the average of everything, which is what our continuum will be. Okay, so it depends on your application and how deeply you want to flag. Now you can see here there's more atmospheric lines, and so again, you want to flag like this. Now, what I should point out is you don't want to just flag up these top points, because that's going to affect your noise properties and it will create some badness in the data. So what you want to do is you really want to select the whole depth in amplitude and just flag completely a given frequency range. Okay, so we're just going to do that here. Okay, so it's working. And we're just going to do this for every single spectral window corresponding to different chunks of the SMA. So this is basically amplitude as a function of channel. Equivalently, we can write, we can show the amplitude as a function of frequency here, which may help you with the line identification. Okay, you see here that there's very high values here near the edge. So maybe we didn't flag enough of the edge. So we could, for example, do this and flag a little more of the edge. There we go. But yeah, so basically this is all error recognition and flagging badness in your data. So this is a function of frequency. Now, the next thing we're going to do is we're going to use plot_ms, but to plot something that we've seen in my non-imaging analysis lecture, we're going to plot okay, we're going to close this now. We're going to plot using plot_ms. Now, instead of amplitude versus channel, here we're going to plot the real part of the visibilities as a function of UV distance. Okay, so that's again the radial plot in UV space that I talked about in my non-imaging lecture. Okay, so here we go. Now this is, I think, is going to take a little bit longer. But basically what this is going to show is it's going to show the real part of the visibilities as a function of UV distance from the phase center of our observations. And this can be used to infer whether you can see some structures already from the visibilities without any need for imaging. Do we see like a point source? Like, is there a strong point source which would look like an offset from 0? Or do we see anything else? So you can see here that the data is quite noisy. So the source will be, if any detection is there, it will be faint, because you can see that the real parts are scattered around 0. But if you have a keen eye, you see that on average, basically these reals are increasing as you get to very small UV distances. So there may be some signal at the shortest UV distances. Now, the fact that there is a varying signal as a function of UV distance is telling you that the source, if any, is probably resolved. Okay, but it's a little hard to do with such noisy, such faint source. Okay, but that just gives you an idea of what you can do with plot_ms. Now we want to continue with continuum imaging, and so what we would do is what I did here is I basically averaged all the data in frequency. So instead of having 1.1 megahertz channel, I averaged all of the frequencies together within a given chunk. Okay, and so yeah, so I'm not going to go through this, but it's basically averaging in frequency just to make the data more easily handled for the imaging step later. Okay, so this is what I did here. Oh, if you have, of course, if you have any spectral line in your data, you're going to want to. Oh, this is what I did here. Actually, let's do it. So if you have any, oh, never mind. We're not going to do it here. But basically, the idea is if you have any, like we did earlier with the atmospheric lines, if you have any spectral lines that actually originate from your source, you're going to want to, and they're strong, so they might affect your continuum. You're going to want to flag them out before continuum imaging. So what I'm doing here is I'm basically creating a continuum MS file, okay, because you don't want to flag your spectral line in your master MS file, because otherwise you will have to unflag it later on for your line imaging. So what I do here is I create a new MS file that I'm going to just focus on for the continuum, flag any spectral line that I see, which I don't need to in this case because this source doesn't have any spectral lines. And then I'm going to average here in these steps. Sorry, these are the steps where I'm basically averaging all the channels together for every given chunk. So you can see here that the width parameter is what's telling me how many channels to average together for every chunk. So 2048 for the first chunk, 2048 for the second chunk, 2048 for the third chunk, etc., etc. Okay, and then and then I check that the output is fine, and and then I end up with basically this this visibility file that is ready for continuum imaging. Okay, so for continuum imaging, we're going to use the tclean task. Okay, the tclean task within Casa is this master task that does all the greeting, weighting, inverse Fourier transforming, the convolution, and then creation of the final clean image. So it has a lot of input parameters. Okay, so one thing you can do in Casa that I didn't mention is you can basically, so if I expand this a little bit, so you can help yourself for any task that you want to run. For example, tclean, you can run help tclean, and that basically shows you all the parameters of tclean, and then it goes on for detailed description. If you press the space bar, you can go down, but let's just run it again. What I find more useful is if you type slash and then you say, I don't know, I'm interested in the weighting parameter and what does it mean and what are the options. Okay, so you would type weighting, and then you press enter. Okay, and that gives us the first instance where the weighting parameter is talked about in this manual file. And then if you press N, it basically goes to the next one and the next one. And that's basically just a faster way to get to here. Here we go. So here's the weighting scheme parameter, and it explains all the different weighting schemes that we have, which you're going to have encountered in your previous lecture, as an example. Another thing you can do is you can use the imp, which means input tclean. And that basically gives you a list of all the input parameters. You can see that there's a lot of standard input parameters here. And as we fill some of these, we will create even more input parameters. But basically what you can do is once you put in, for example, your vis, which is your input visibility file, you can just say, okay, vis, I would have done this here, vis equals to this one. Okay, so this is the visibility file that we want to image. Okay, and so once you type that now, you can type imp again. And what you will see is that it will have filled the field of the parameter that you've just described, that you've just given, that we've just assigned to something. Okay, so you can do this to basically get an idea of what's selected for every single parameter within tclean, and I find it quite handy. You can also do it in a scripted way, like I'm doing here in the script, and where I'm kind of describing what each of the things are. But you can always use the help to help yourself. So, okay, so the first thing that I define is the file names. So the vis, as I said, is the input visibility data, which is just this MS file that I chose here, which is the channel average continuum file after all the flagging and inspection. And then I have an image name, which basically tells me where do I want to put my image, what address, and what do I want to call it. And usually I call it something like that has underscore my weighting scheme and underscore cont to indicate continuum, just so that I can track what each image contains later on. Okay, and then there are some imaging parameters. Okay, so the first parameter is this interactive dot equals to true, which basically, if you remember about so if you remember our process, so it's basically what's going to happen is that for every cycle, or for every few cycles at least, it's going to show us a residual image, and it's going to stop and ask us, do you want to go further and deconvolve a little bit more, or are you happy with it? Okay, because if you set that to if you set that to false, then it's not going to ask you, and it's going to continue cleaning for a certain number of cycles that you determine here. So n iter here is the number of iterations before stopping the deconvolutions, which you can set automatically to a value. Here we have a very big value, but in this case it doesn't matter because we've set interactive to be equal to true, so it will stop every certain at every iteration basically. So this n iter will be ignored, but we just set it to a large number there. So So cell will be your pixel size, okay, the pixel size of your image. Remember, we choose our own image pixel size. So how do we choose it? We typically want it to be a small fraction of our expected beam size, okay? So if our synthesized beam with the SMA is typically a few arc seconds, well, depending, it could be a fraction of an arc seconds if we're observing an extended or vex configurations. You want that to be about a third, at least at most about a third of your beam. So here we choose select 0.1 arc seconds, which is definitely small enough because we expect this data, this configuration that this data was taken in to give us a few arc second resolution. Okay, then the image size basically tells us how many pixels we're going to have along the RA and deck direction. And so we want to make sure that that's enough to cover the primary beam of our data. So in this case, we will get an image that is about 51 arc seconds by 51 arc seconds, which should be sufficient. Then we've got our weighting. Which weighting scheme do we want to use? In this case, natural weighting. If the weighting is Briggs weighting, we can set a robust parameter. I'm not going to go through the weighting again because you will have seen it in other lectures, but this is where you would set it in the T-clean task. And then a UV taper if you want to apply a UV taper as well. Okay, so for continuum imaging, you want to use spec mode equals to MFS, which means multi-frequency synthesis. Okay, and that's just saying we want to do continuum imaging, basically. Then there's a number of parameters which are basically parameters that are used for the gridding and to choose a different deconvolution algorithm. So in this case, we want to use a standard gridder, which is the one that would have been described in the imaging lectures, and then a classic Hogbone 1974 deconvolver. And now these are all parameters that I've left as the standards that are used in a T-clean call. So if you call it without describing these parameters, it will use these exact parameters here. So you don't really need to play with those normally. But for example, the gain is the loop gain that we talked about, gamma here. Basically, it's basically what fraction of the peak is inserted into the model image at every iteration. Okay, and you can set different thresholds, which don't really matter here because we're going to do clean in an interactive way. So we're going to decide ourselves how many more cycles to do at every time. Okay, so these are just some standard parameters. Now here I'm going to basically remove images if they already exist, because if you run T-clean with an image name that is equal to an image that already exists, it will continue the deconvolution basically where it stopped. So it's always, I find it always handy to have this little command here, although be careful because it can remove images that you might actually want to use. Okay, so we're going to run that. Just delete any existing images. And finally, we're going to run the T-clean command with all our parameters that we predefined. Okay, so you'll see now in the log, it is. Yeah, you can see that the task has begun, T-clean, with all of these parameters that we inputted, or standard parameters if we didn't input them. It selects a certain number of rows, basically it starts, and it basically starts by making the PSF. Okay, so the first thing it's doing is it's creating the dirty beam. So that's what the PSF is in our case. And in creating this dirty beam, it's telling us that the core of this dirty beam is about 4.3 by 3.6 arc seconds with a position angle of 51 degrees east of north. And so that will be our dirty beam. And it's also telling us from the weights and the visibilities and the weighting scheme that we chose, is telling us that the theoretical sensitivity we should expect in the center of our image should be about 75, should be about 0.07 millijansky, which actually looks pretty small. So we'll see how that compares. Right. Okay, so then it ran a major cycle, but you can see that it didn't put anything in the model. So right now, what it's going to present us with is the dirty image. And in fact, that's exactly what we see. I should say that in the terminal here, basically printed as some progress. I find it interesting that it basically gives us from 0 to 100%, but then does it again. So it's not really 100%, but anyways, it's probably 100% of making the PSF and then 100% of doing the first inverse Fourier transform to get the dirty image. And indeed, you can see that it printed the first dirty image of our data here. Okay, so this is the interactive mode. So we can see in the GUI, in the viewer GUI, we can see the dirty image. And now what we're going to do is going to draw a mask, as I mentioned before, to select regions where we think there is a source. Now, when you take an observation, you always have some a priori information on what you want to observe. Okay, so in my case, in this situation, I wanted to observe a belt, or a dusty belt, so a circumstellar disk around a nearby star, and this circumstellar disk is at a certain distance from the star and is expected to be resolved at the center of the image. So the observation was centered at the location of the star here. Okay, so what I see now then is I see some elongated structure in the northeast-southwest direction, which with my a priori information, this should be a belt around a nearby star, I interpret as likely to be a belt viewed edge-on from Earth. So whereas a ring can be seen face-on from Earth, it can also be seen edge-on, which will cause these two announcements at a distance from the star equal to the location of the ring. So I concluded that's probably in the center emission from the belt that I'm looking for. But I also see there's a bright source here to the side. So that's probably, you can see that the signal to noise is quite high, like its brightness looks quite high compared to the background noise. So it's probably real. And it turns out that this is actually a background galaxy that just happens to be within the field of view. So but what we're going to do is basically, we're going to draw circles, we're going to draw regions around locations where we think the emission is true and astrophysical in nature. So we don't want to draw these masks around noise regions. So you need to be very careful and only really draw them around regions that you really think there is some significant signal. So for example, it's pretty clear that there's some significant signal here, so I can select a circle here and draw a circle and then double click to confirm that this is the mask that I want. You can also draw irregular shapes using this command, and I draw an irregular shape here to comprise the region around the central star. Okay, here it is. You can see that I kind of made a mistake here. Maybe I want to make it a little wider, so I can drag these points and fix it up, and then double click it to when I'm happy. And this doesn't really matter too much where you draw this region, but you generally want to comprise your source and enough of a region around it. Okay, but you can modify these masks as you go along at every cycle iteration. So let's just remind ourselves of what's going on now. So what's going to be going on now, we're in the deconvolution stage. So we've created this first dirty image, and now we're going to basically, the clean algorithm is going to choose the peak flux within our masks, which is going to be here in our case, and then put a fraction of the flux in our model image, convolve that model image to create a dirty model image, and then subtract that from our dirty image to get a residual image. So that's what we're going to do. Now, to speed up the process, you can tell it how many cycles to do all at once before presenting us with a residual image again. And in this case, I'm going to select 10 cycles. So I tell it, please do 10 cycles of removing emission before you present me with a residual image again. And once I'm happy with it, I just press this button here, the green arrow. Okay, and you will see now if we bring back the log, you can see that it's running minor cycle iteration, and you can already tell that in this cycle, what it did here 10 iteration. So it went from iteration 0 to 10, and basically added this much flux to the model. So it basically added, this is in Jansky, so the model went from having 0 millijansky, so empty model, to having 1.1 millijansky, and the peak in the residual image went from 1.5 millijansky down to 0.7 millijansky. So we're removing emission from our dirty image and putting it in the model. Okay, right. So it completed 10 iterations and it's happy, and it brought us back a new residual image with that flux removed. Okay. So you can see that most of the flux is being removed from the brightest source, because naturally clean always finds the maximum within your masks. So obviously it will go there first. Okay, so we can still see that there's probably still some significant emission here. And what we want to do is basically we want to continue repeating these cycles. You can obviously change the number of cycles here in this interactive mode. You can decide, okay, I don't want to quite do 10 more. I want to do maybe 5 or or this is too slow, I want to do 100, and you know, adjust it as you like. You can also adjust the masks. You can remove a mask by basically drawing a circle around the current mask, and then if you click erase here, you can double click and then it removes your mask. Okay, and I'm just going to add it again because I think there's still probably some emission there that we could be cleaning. Okay, so we're going to just do that again. And again, if we look at the log, if we look at the log here, it did another 10 iterations, okay? And the model went from having 1.1 millijansky to having 1.76 millijansky. So that's that's our model, clean model. And the peak residual still decreased down to 0.5, from 0.7 to 0.5 millijansky. So we're removing still flux from the image within these masks, wherever the peaks are. Okay, so we're gonna wait for it to finish, and it presents with the residual image again. Now at this point, you might choose, you might say, okay, is there still, does this look like noise, or is there still signal that is probably astrophysical, even though a low level that we could still continue cleaning? And it's hard to say, right? Because there are some peaks in the noise that are at the same level of what we think is our astrophysical signal. So we could probably already stop here, but we're going to go another 10 steps and continue in this case. Okay, so we're going to do another 10 steps, and you see the flux went from 1.8 to 2.1 millijansky, and the peak went down again, and completed 30 iterations in total. Now you will have seen that there is potentially a source up here, but since this is far from the center of the field, where the sensitivity of the primary beam, the sensitivity of the response of the antenna is low, then we want to be a little bit careful about selecting emission there, especially since we don't expect any source to be there. There could be another background galaxy, but we're just going to leave it there. Obviously, you can play with your cleaning. You can create different images, one where you basically add an extra source here, one where you don't, and compare the results to try and understand whether that is physical or not. But you can see it's at a very low sigma level. Okay, so now we get an image that if we got it to begin with, we might just think, oh, this is just noise. Okay, if I weren't drawing these masks, so we are satisfied that our residual image just looks like noise. Remember, as we were saying in our process in the slides, when we're satisfied that this is noise-like, okay, we can say yes, okay, we're happy, and so we tell clean, we're happy to stop cleaning. So we're going to click the big X, and you can see the terminal brought us back to the IPython here. So we have concluded our clean. Okay, so what we're going to do is we're going to click Viewer to reopen the viewer and view our result. Okay, what we will find is that the tclean command hasn't created just a single image. Here we go. Okay, so the data, we've put it in here. Okay, so it's create all of these images. So you can see each of this file is an image within this directory. And so it's created, this is our final result, okay, which we'll wait a second to create. So it created also an image which contains our masks. Here it is. You can see that these are basically the masks that we've drawn in the deconvolution process. Now, if we've changed the masks over time, remember, you can, at every step in the iteration, you can change your masks. It will only show us the latest masks that we've actually used. So this can be useful, but it depends how much you play with your masks during the cleaning. And remember, if you're doing line imaging, which we won't have time to do today, but if you're doing line imaging, what's going to happen is you're going to have to clean every single channel and draw potentially different masks in every single channel. So, and then we've got an image called .model, and that .model image contains, I'll just click here, yeah, contains our clean model, which is kind of hard to see. I'm going to try and zoom in. Oops. Oh, that closed it there. Don't know why, but okay. Gonna reopen the viewer. Sorry about that. Okay. Okay, we're opening our model image, and you can see that the model image is kind of hard to see, but basically it just contains a pixel here with some flux, a pixel here with some flux. See, can I just do that? Yeah, okay, it's more obvious there when I zoom in. Pixel here with some flux, you can hover over it. That's with 0.5 millijansky of flux. A pixel here with 0.4 millijansky of flux, and the pixel and oops, to draw this region, and a pixel here with a bit more flux again. So basically, again, clean creates a model that is a sum of point sources. So it basically chose that there were 2 point sources here and here along the elongation of what we think is an edge-on disk, and there's a point source here as well. Okay, so that's our very simplified clean model. Then the other things that tclean returns is the .pb image, which is an image of the primary beam of our observations. So this is the response of one of the SMA antennas, where it's 100% at the center and then decreases towards the edges. Okay, so you can see that it gets to about the half power about here, where the peak says 0.5 as we hover it. Okay, and so yeah, so that gives us our primary beam. Then there's the .psf, which gives us our dirty beam. So this is the dirty beam of our observation, and you can see that the clean beam is basically the core of this dirty beam, and this dirty beam has a significant amount of structure around it, which is caused by basically our incomplete SMA UV coverage. So this is simply the inverse Fourier transform of the UV coverage of our observation, and then finally gives us the residual image if we wanted to look at that again, just to make sure that in future, if we want to make sure that we clean deep enough. Yeah, and this looks quite like noise, so we're happy enough with it. And then there's a dot sum weight image that we don't really care about. But let's look at our final result. Okay, here's our final result. Okay, so here's our final clean image. It still looks very noisy because we're looking at faint targets in this case, but it will basically have worked to improve the images, and in particular to basically bring all of the flux that would have been in the side lobes in the initial dirty image. It would have brought it in at the location of these sources that we have identified. So that's the end of the clean process. You will see that this effect of the cleaning is much more obvious if you have higher signal to noise images, because this image unfortunately is dominated by noise because the sources are quite faint. We're only talking about a few millijansky, but nonetheless we can conclude that we've detected a point source here, and that we've detected some elongated structure along the northeast southwest direction here. Now, if I didn't have any a priori information that this is a belt because I have an infrared excess and I know at a priori what I want to observe, then you may have concluded that there is a couple of point sources near the center of the image. You cannot distinguish unless you have any a priori information within this data. But of course, if your data is much higher signal to noise, it will of course look much better. And this down here is the clean beam of our observations. Okay, great. So I hope you enjoyed this Casa Clean tutorial. I don't have time to go into line imaging, but you can look at this script here where I use an example of a different data set, and basically I go through what you would do for line imaging, including continuous subtraction, and then different parameters to choose for T-cleaning, in this case for a 12CO line, but applicable to any other line that you're interested in. So this may be useful to you, and this script will be made available to you for the imaging during your data reduction section, and later on if you need it for your own SMA data. So I hope you enjoyed this little tutorial, and good luck with your data.